And we are going to finally get into CFT measurements. So let me change my color of my pen quickly here. Let's do that. We're going to get into continuous Fourier transforms, CFT. Again, the goal of continuous Fourier transforms, we take an original signal, so y of t is a function of time, some signal, again, it could be periodic, it could be aperiodic, it could be random, et cetera, but it will repeat over some period t, and we're going to take this signal in time space, we're going to develop a frequency spectrum, so we're going to perform a continuous Fourier transform. We are going to calculate harmonic coefficients a sub n, b sub n, and then calculate c sub n. We are going to plot a frequency spectrum, so the magnitude of our harmonic coefficients as a function of frequency, where each of kind of these points will correspond to some frequency. So the fundamental frequency 1, 2 times the fundamental frequency, f, et cetera, where we multiply all the way to n delta f, our maximum frequency that's determined by the number of harmonic coefficients. So our fundamental frequency will be the lowest frequency in our system, the maximum frequency will be here, and then the dominant frequency will be the one with the highest amplitude. So this is the key kind of analysis tool, so that frequency spectrum, that's what we're going to be kind of using as our kind of engineering toolkit to design materials, to design systems in order to kind of avoid certain frequencies that we want, or to kind of amplify signals that we want to, or just to analyze signals, again, all the examples that we talked about previously. And at the end, you can perform, we can write out our Fourier series and basically approximate this signal, our original signal, y of t, so that plot we see above there. We're going to approximate it as a series of infinite sines and cosines with due to these harmonic coefficients. But again, we'll get into that a little bit later. So back to, here we go, what we're going to talk about today. So in lecture 1, we talked that we could have signals that are static, dynamic, periodic, aperiodic. And the beauty of Fourier analysis is that it doesn't matter. We can basically analyze any signal we want using the framework that we're going to kind of present here. Now, there's lots of resources online, lots of different Fourier transform codes and notation. It can get very confusing, my notation versus notation you might see elsewhere. So I would suggest in this class, just be consistent with this notation unless it really doesn't work for you, and we can kind of discuss alternative methods in case this really doesn't make sense. But anyways, the key thing, we're going to get into a lot of math right now, or some math. Don't get lost in the math. Keep that general kind of conceptual fundamental ideas of Fourier transform that we talked about in the last series of videos. So many of the signals are going to be periodic, and some will be harmonic functions. So I hope, or I guarantee you've all encountered some harmonic functions before, but maybe, hopefully, you've seen a function like this, either sine or cosine, just periodic signals. But we can actually mathematically describe if a function can be classified as harmonic. So if I have a function y of t, it is harmonic if the following conditions are met. So if I take the second derivative, I recover my original signal, and it'll just be minus some constant c. So why don't you go ahead and prove, so on your own time, cosine and sine are harmonic functions. Is x squared a harmonic function? So you could go ahead and calculate that out in Mathematica. So these harmonic functions are just functions that can be treated over some period. So they repeat. So for example, in this signal, it repeats after it comes. So we go up, and down again. It repeats over some period, some arbitrary period, t here. So this would be, it repeats over some period t, and they're typically going to exhibit some type of frequency. Again, because they repeat, they're harmonic. They repeat as a function of time, and we are going to distinguish between two critical types of frequencies. Again, that hopefully you've already run into before. So circular frequencies and cyclic frequencies. What are my units of circular frequencies? Waiting, rad per second. What about cyclic frequencies? Hertz. So in this course, we always want to deal with cyclic frequencies. So we want to write everything in terms of cyclic frequencies. Unfortunately, a lot of the times when you're given functions, it's me giving in terms, again, your default when you're dealing with sines and cosines, especially unless you're in degree mode, you're going to be given the frequency in terms of omega. So we need the circular frequency. So we need to convert between the circular frequency, which is typically what we're given, to the cyclic frequency Hertz values, which we want to work with as engineers. So luckily, you could look up, there's this Yoch, there's these Yoch stock mechanisms. You could Google on YouTube to kind of see how cyclical frequency and circular frequency relate, but I hope that people have run into this equation previously. So that's how we can relate our circular frequency to our cyclical frequency. So that's just, again, equation we need to have in order to kind of analyze this. We're going to introduce a couple, in continuous Fourier transform and discrete Fourier transforms, there's lots of equations, but there's going to be some fundamental relationships that we need to basically have at our hands at all times that we don't even have to look up, so we could solve problems, efficiently, quickly, and correctly. This is one of those kind of key expressions. So I'm going to start to star some that I think are really, really important as we go through these lectures. So we already answered this question. We didn't even have to look at these notes. But yeah, harmonic functions, again, we would just discuss this previously. So now we're going to get into the calculations and the math of continuous Fourier transforms. So the key part to begin our CFT, our continuous Fourier transforms, is we need to calculate the harmonic coefficients, A sub n and B sub n. Again, a lot of math is coming. Don't get lost in the math, high-level conceptual understanding. So we can do, when can we perform a continuous Fourier transform? Because we're going to start to talk also about discrete Fourier transforms. Well, we can do continuous Fourier transforms when we have the algebraic expression of our signal, y of t, that original signal that we're wanting to work with. So if I know y of t, for example, equals cosine of t, I know then I can perform a continuous Fourier transform. Discrete Fourier transforms are more appropriate if I just have like a set of data, right? So if I just have points and I don't know what the, this function, or I can't describe it algebraically, I have to do a discrete Fourier transform. But if I know, or if I can write the expression, the algebraic expression for my function, then I could do continuous Fourier transform. So remember, we're going to transform it from time space to reciprocal time space or frequency space, and we're going to calculate basically our Fourier series, the harmonic coefficients, A sub n, B sub n. So they're going to vary at different integer values. So we're going to talk about how we kind of describe and refer to these harmonic coefficients in a second, but we vary, n goes to, as you can see here, 0, 1, 2, all the way to infinity for, this is again, these limits are specifically for CFT. But again, this is a beautiful kind of, we could represent any arbitrary signal, y of t, as this infinite series of sines and cosines, and we could, again, create this frequency spectrum. So let's figure out how we calculate our harmonic coefficients. So this is, again, where the math gets a little bit confusing. So this is our fundamental expressions for how we calculate our harmonic coefficients for continuous Fourier transforms. So I have to take the integral, so omega, pi, the limits of integration. I'm just going to integrate my y of t times cosine omega n t, my y of t for this, and I'm going to plug in and keep this general. I'm not going to solve for n. I'm going to integrate first, and then I'm going to plug in for different values of n. And each of those values of n corresponds to different harmonic coefficients in, y of t is our original signal, etc. So if I ask you for the third harmonic coefficient, I'm saying n equals 3. So I'm looking for a sub 3 and b sub 3. If I ask for the fifth order harmonic, then I'm looking for equals 5, and et cetera, and et cetera, and et cetera. So the key part, and we're going to see this in a second, in order to approximate your signal better, we want as many harmonic coefficients as possible. So we could, if we go to infinity, we could exactly replicate any signal that we're given. But obviously, mathematically, we can never really get to, maybe mathematicians will argue, but anyways, so we're going to have to calculate for different values of n. Or, better said, we're going to increase our harmonic, again, this is kind of what we were talking about just previously. So what's the issue when the expressions that we have above? We don't want to work with circular frequency. We want to work with cyclical frequencies. So I want to substitute in and use this relationship. We also know, and we've kind of discussed previously as well, that there's going to be some, even if the signal is, aperiodic, there's going to be some period t over which this repeats. So I know that if I have a signal that repeats over some period t, the lowest or the fundamental frequency of any signal will just be 1 over that period. This is another star equation. So this is really, really critical. The lowest frequency, my fundamental frequency, delta f, is essentially just going to be, is equal to 1 over my period, capital T. So if I substitute that back into my expression, so if I plug in, if I want to look at what circular frequency corresponds to my lowest fundamental frequency, I'm just going to kind of plug this expression into here. Again, this isn't too critical yet, but it's just for to kind of rewrite this expression in terms of my fundamental frequency, that f. Anyways, so now what we're working with here is we're going to rewrite our expression now in terms of, effectively the fundamental frequency, because you can see here 1 over t is equal to delta f. So more on that a little bit later. So let's go ahead. So I'm going to use this expression. I'm going to plug that back into what we saw previously. So I'm going to plug in for omega. So we just saw that omega equals 2 pi t, or 2 pi over t, excuse me. Equals 2 pi t. So if I plug in here, so I have 2 pi over t pi. So this cancels, this cancels. So this becomes just 2 over t. And in here, I have 2 pi divided by 2 pi t. So cancels. So you see now the limits of integration change here, and you plug in for there. Just plug and chug. And now we get to this expression. This is the expression that we want to work with. I want to always, always, always work. When I want to calculate my harmonic coefficients for CFT, this is the equation I want to use, nothing else. And you can kind of see in here, hidden, and we're seeing a little bit, that you could rewrite this in terms of that delta f. But again, I prefer this notation. I'll introduce the other one, and if that helps you kind of understand or kind of visualize what's happening. But this is the notation that we want to work with here. So once we have our harmonic coefficients, in order to create our frequency spectrum, we're going to plot the magnitude of these harmonic coefficients, C sub n, which is just, again, magnitude here. And we're going to plot it as a function of integer values of the fundamental frequency f, so, or the delta f. So we're going to plot delta f. So n equals 1, and that's a lot of information here. At n equals 1 or n equals 0, what is our delta f? So it's like n times, you could rewrite, look at this expression, it's like 2 pi n delta ft. So for my first harmonic coefficient, it's just going to be f, 1 times delta f. Second harmonic coefficient, 2 times delta f, et cetera, all the way to n times delta f. So at each of these frequencies are going to be a different magnitude, and we're going to figure out lowest frequency, highest frequency, dominant frequency. That's the whole goal of this frequency spectrum here. So that's a lot of information to take in, kind of conceptually. The best way to kind of work with these problems is to do an example. So we're going to get into that in the next video. All right, thanks. I'll see you all next time. And next time it'll be hip to be square. Please, Huey Lewis, do not sue me. Thanks.